Perfect. So, hi everyone, welcome. I think while we wait for more people to join, I think we're going to start with one quick question. Um, of all the people who has joined, could you please answer in the chat box whether you are aware or you understand what technical debt is, and whether do you use any tool uh, in your organization or in your ID to detect technical debt, right? So what you could do is maybe simply in your chat box, you can say, yes, you understand technical debt. And if you use a tool, you can just type in a name. So you can say, yes, Sonar, or yes, I don't know, PMD, find bugs, whatever you may be using. So I'm going to go ahead and start with it. I'm going to say yes, along with the tools, Sonar and CodeScene that we use. So Adam, I see that there's some people who are using Infer, which is a Xcode static analyzer.
And that's an interesting one. I've never came across that one. And Sonar seems very popular.
Yes. So we have one person who said they don't know, but they're excited to learn what technical debt is. Yep. I think so. I think there's a kind of a statutory warning here. A lot of people are from eClinical Works over here, and that's why you may see similar answers, especially about Sonar. But nevertheless, I think Sonar is one of the de facto standard in the industry when it comes to I don't know whether to call it technical debt, but to at least scan code smells and vulnerability and OWASP top 10 issues and whatnot, right? I think that being said, I think it's almost 1:34. Let's start the talk. Today we have so hi everyone. Today we are going to talk to Adam Tornhill. I came to know about him first when I read an excellent book written by him, Software Design X-Rays. That was my first encounter with the reality of technical debt and its prioritization. And yes, tools like Sonar can scan all the possible, let's say you're doing code scans using Sonar, one of the tools that's been coming up a lot over here. But you do a code scan using something like Sonar and it says, hey, this could be a possible null pointer exception right here. But Sonar can't really tell you if there are possible null pointer exceptions across 5 different kinds of files, or 5 different files, or 10 different packages. So Sonar doesn't help you prioritize technical debt where you need more attention and where maybe you don't need enough attention. And that's where the tool that Adam has created is really useful. He's also a co-founder of CodeScene. It has been helping organizations like eClinical Works understand technical debt better. After we used it in eClinical Works, we understood that technical debt is not uniformly spread in your code base, but rather it sits in clusters. And today we are going to talk about how to uncover these clusters and measure, visualize, and prioritize technical debt with behavioral code analysis. That being said, I'll be passing the baton to Adam. Go ahead, Adam. Thanks a lot.
Thanks a lot for that wonderful introduction. And hello, everyone. Really nice to be here. Now let's see the main challenge of sharing my screen. So please let me know when you can see my screen and I go ahead. All right, everyone can see it. Perfect. All right, so I'm going to talk about how to measure, visualize, and prioritize technical debt. And I'm going to use a technique known as behavioral code analysis. And I'm going to explain what that is. But before I get there, maybe a little bit about me. So I'm an engineer by training. I'm trained as an electrical engineer, but I also have a second degree. I have a second degree within psychology, and psychology happens to be one of my big passions. It's one of my big interests. And what I've been trying to do is to take my psychological perspective and put it on top of my technical background. So I come at software from a very different direction. And as mentioned in the introduction, I've written 2 books about this intersection of psychology and technology. The first was Your Code is a Crime Scene that came out, I think, 6, almost 7 years ago. And the new book is called Software Design X-Rays, which is a follow-up and a deeper treatment of the topics from Your Code is a Crime Scene. Now, before I move on, I would like to explain why I got interested in psychology in the first place. So I joined my first work as a software developer in 1997. So it's been a long time already, hasn't it? And I joined a fairly large organization. And what surprised me was that everyone was so incredibly busy, right? So I joined as a newcomer and no one really had time to onboard me. But everyone promised that in a couple of weeks, the situation will be much, much better. In a couple of weeks, we will have time to sit down with you and explain everything and give you a proper onboarding. So I thought, wonderful. What's going to happen in 2 weeks? Well, what was supposed to happen 2 weeks later was that at this time, the organization had been building a new system. That new system involved new hardware components and at least 4 to 5 different subsystems in software, completely developed from scratch by a bunch of different teams. And they could actually see the end of that road now because the only thing remaining, I repeat, the only thing remaining was to integrate it. As you can imagine, integrating development and hardware work done over a couple of years within 2 weeks just didn't exactly go that smoothly. In fact, 6 months later, the whole project had to be, canceled and restarted with a new scope because we could never get that to work. And that kind of got me interested into why do we keep making mistakes like this, right? I had a lot of smart colleagues, some really smart colleagues, and yet we keep ending up in these situations because this initial experience, which was my welcoming to the software industry, was not exactly something unique. I've seen similar patterns happen over and over again over the past 2 decades. So at some point, I really wanted to question that. I wanted to figure out why is it so hard to succeed with software at scale? And I decided to look into psychology because psychology is largely about people like us, people who develop software, how we think, how we reason, how we solve problems, and also how we work with others. And initially, I just wanted to sign up for an introductory course at the university, but it turned out that psychology is really fun. So after I completed my first year, I thought, all right, let's do 1 more year so I get the chance to dig deeper. And after that second year, I realized that if I do 1 more year, I can actually get my bachelor. And after my bachelor, I felt like I'm close to a master degree now, right? So I just moved on. So one could say that I took my psychology degree more or less by accident. I didn't plan for it. But anyway, that's why I got interested in this stuff. And you might actually ask, because there are many people that think that I'm some kind of manager who kind of comes from the side that don't write code myself. But I'm actually very interested in programming, and I program almost on a daily basis. And in addition to my books on technical depth, I've also written 2 more technical books. The first one on using design patterns in the context of the C language. And the second book, which is my favorite, how to use Lisp, this amazing programming language to build web applications. Okay, you might ask, but do I actually have any code to show to kind of support my credentials here? Well, let me show you the piece of code that I'm most proud of. So this is code that I wrote a long time ago. It's public here on my webpage. And what I did here was that I tried to tackle this interview challenge of solving FISPAs. And I decided to do it in C++. And what I like about that C++ code is that it's not even valid C++. That means you cannot compile it. But as it happens, as a side effect, when the compiler fails, it outputs the solution to the FISPAS challenge in its compiler error messages. So if you're into this stuff, please have a look at the article, a link here at the bottom. All right, that was me. Let's talk about us instead. let's talk about software development. Why is it so challenging? The reason I think software development is so challenging is because reality to us humans, it's largely a Rorschach blot. And I would like to read a quote for you from one of my favorite psychologists. This is a psychologist called Bars, and he made this statement that humans, we seem to be driven at least as much by fantasy as by reality. And what that means in practice is that when we as humans, as software developers, are in doubt about something, our experience and decisions are driven by largely completely unsupported expectations, right? When we lack data, we kind of fill in with certainty, but it's based on speculation. And this can very easily bias our discussions and decisions. And I would like to show you how easy that is by taking you to one of my favorite psychology experiments. So this is an experiment that was performed in the 1970s. And the challenge here was that they had two groups of participants in that experiment. One group was based in the south of Britain, and another group was based in the north of Britain. And their task was to simply draw a map over Britain. What does the geography look like? What does Great Britain look like? And these are the two maps that they came up with. One to the left, one to the right. Which one of these maps do you think was drawn in the south? Yeah, that's right. This one. And as you can see, the participants that were located in the south of Britain, in Cambridge, as you can see, they aggregated all distances in the south, which coincidentally happens to be the area of Britain that they are most familiar with, because that's where they live. The participants in the north, and you see their map to the right, they made the opposite error, of course, right? They underestimated the distances in the south, the area that they were less familiar with. And when I learned about this stuff, I started to think, hey, this is about humans after all, right? What if we have the same kind of biases within software? What if we too overestimate the importance of the parts of the code we are familiar with and underestimate the importance of the parts of the code we are not familiar with? What's the consequences of that? Well, the consequences of that is that we will lack what I call situational awareness. And why is situational awareness important? If we consider our modern software systems, we see that a modern software system is incredibly complicated. I have more or less noticed that over my 2 decades in the software industry, that the systems I worked with 20 years ago, they were complex for sure, but they were much, much simpler than today's systems. Because today's systems very often are built as a system of systems, right? So we have multiple different software units, multiple different subsystems that kind of need to integrate with each other. We might have multiple databases, and we very often have multiple clients, right? We have all our smartphone apps, we have a desktop application, we might have a REST API, we might integrate with other systems. And what this complexity means to us is that a software system today is simply so complicated that we as individuals cannot keep all of that complexity in our head. And that means, again, that if we want to reason about things like technical depth or how to improve developer efficiency or how to deliver faster, it's going to be incredibly hard to have those conversations because, again, our experience will be heavily biased with the parts we are familiar with. And this lack of situational awareness makes it very hard to deal with technical depth. So let me give you a brief introduction to that topic, and then we're going to jump into some real-world code bases and see some real examples. So let's start with the definition of technical depth. And I think this is important because my experience is that we, as software developers, we have as many definitions of technical depth as there are conference speakers and books, right? So for the purpose of this talk, the way I define technical depth is that it's basically a metaphor that, just like its financial counterpart, it means that we take on some kind of depth And that debt means that we get to pay an interest on it. So why do we do that? Typically, it's because we want to get some kind of benefit in the short term. And the typical scenario is that we have a customer and they really, really need a particular feature. And we know that our design isn't really up to that, right? We would actually need to change some fundamentals in a software design to deliver that feature safely. But we also know that that would take a couple of weeks, maybe even a couple of months. So let's do a quick and dirty solution here. Let's hack in a bunch of if statements and treat this as a special case. And maybe we can get this feature out the door next week already. That's great. Happy customer, happy product owner. Everyone's happy. The problem now is that we have taken on technical debt. So the next time we need to modify that part of the code where we did a shortcut, it's going to be more expensive and it's going to be higher risk because the code is now harder to understand. So to me, technical debt is code that's more expensive to maintain than it has to be. What are the consequences of technical debt? Well, there are lots of them, and I tried to summarize the most important ones for you here. So let's have a look at this list, and I will go through it briefly. First of all, I like to point out that technical debt is a very, very real problem. And it has grown in importance because it has received so much attention over the past year. And the reason for that is that because many software development organizations are wasting a lot of their time dealing with technical debt. And there are some pretty good research numbers here that shows that somewhere between 23 to 42% of all development time is wasted due to technical debt. So if we take a step back and consider what that means, it basically means that if we have an organization with 100 developers, with a high degree of technical debt, we're getting the equivalent of 60 developers out of that organization. And the rest of the capacity is simply wasted. So why do we end up in those situations? I think that it's mainly because technical debt lacks visibility. That means, you know, if we have a code base, we cannot pick it up, turn it around and inspect it for flaws. Software lacks physics. And this makes it very, very easy to miss the real root cause. What we tend to see instead, if we have a high degree of technical debt, is that we experience symptoms. And the symptoms that we typically experience are...
Sorry,
Should I go ahead? Yeah,
yes,
okay,
yes,
good, good. Okay, let's see if I can pick up my track here again. Yes, we tend to experience symptoms instead of the real root cause. So what you typically see is that your lead times for implementing a new feature, they get longer and longer and longer. So 5 years ago, you could implement something in a couple of days. Today, it might take you 2 months, right? Those are very typical symptoms of growing technical debt. As a consequence of that, our development also tends to get much less predictable. I mean, software estimation is a black art at best, right? And with a high degree of technical debt, it becomes virtually impossible to guess when something will be done because there's such a huge amount of uncertainty, right? And for us as developers, it also has a very direct impact because technical debt makes our work much less enjoyable. Instead of being proactive and work on delivering new cool features to our users, what we do instead is that we become a very reactive organization, right? We act on failures all the time, and our workday becomes very unpredictable. So instead of moving ahead at a good pace with new features, we might end up, working and investigating 5 different support tickets, and at the end of the day, we haven't really moved forward. So technical debt has a very real experience, a very real impact on job satisfaction as well. Now, the last 2 points that I want to cover here before we get into some real world case studies is that I want to reflect a little bit on static analysis that I know that many of you use. And that's good. I'm using static analysis tools myself. I'm a big fan of them. And I find that static analysis is very valuable when writing code, right? It can work as a low-level feedback loop for me as a developer. However, what static analysis is not good at is to identify and prioritize technical debt. And the reason for that is because technical debt is simply not within the scope of a static analysis. It's impossible with static analysis. And the reason I say this is because technical debt just cannot be detected in the source code. Just because some code is overly complicated, that doesn't mean it's technical debt. And I'm going to get to that. It also doesn't mean that the cost of the technical debt is the cost to fix that source code. It's not. That's the cost of the refactoring. But the actual cost of technical debt is how much longer it takes you to implement a new feature, how much rework you have, factors like that. And those factors are simply invisible in the code itself. So what I hope to have achieved at this point in the presentation is that I hope that I've created awareness of why technical debt is relevant and why it's important to keep track of it and manage it. Now, let's look at some possible solutions. What I want to focus on is what I call a behavioral code analysis. And a behavioral code analysis differs from a traditional code analysis in the sense that it focuses more on the behavior of the development organization rather than what the code looks like today. So in the behavioral code analysis, the code is important, right? It's one important input, but it's even more important how that code impacts the development organization and how the organization works with it. And I hope to clarify that once we get to the real world examples. Before we do that, I also like to point out, I'm always trying to be very clear about this, that I do think that behavioral code analysis is something that every single company, every single software company should use. But I also want to point out that I don't view it as any silver bullet. A behavioral code analysis is also not intended to replace anything, except for maybe speculations, right? And unexpected rework. Instead, the way I view behavioral code analysis is as a complement that can help you focus your existing expertise, your attention to the parts of the system that are likely to need it the most. So with that introduction, let's look at some real code bases and see if we can identify any technical debt, and more important, how we can prioritize it. So I'm going to shift to Chrome. Here we go. And you should now be able to see my browser window here. What you see on screen here is an analysis of a project called React. So React is a UI library developed by Facebook. It's very, very popular in the web development world. And many of you are most likely familiar with React as users. So today we're going to look a little bit under the hood. The tool I'm using here is CodeScene, which is the world's first behavioral code analysis tool. And it's something I've been working on for the past 5 years. Now, we see here that the only thing I've done so far is that I pointed CodeScene to the React Git repository, and then I pressed a button. And then I got this analysis. And we see that there's a lot of data here. It can easily feel a little bit overwhelming at first, but we're not going to focus on all of it. What I want us to focus on is technical debt. And let's start by trying to get situational awareness. And in behavioral code analysis, the main technique is something called hotspots. So let's look at the hotspots in React, and I'm going to explain what a hotspot is and how you use it. So if I click this button, you should see something now that looks like a Petri dish, almost like a bacteria culture, right? But it's not. This is 400,000 lines of code. This is the entire React code base visualized. And the way you read this visualization is that each one of these circles, the large circles you see here, the ones I'm hovering over, they represent a top-level folder in that Git repository. So that means that if this was one of your code bases, you would recognize the names of those folders as important subsystems or high-level components, right? So it's a visualization that always follows the structure of your code. It's also interactive, so I can zoom in on the parts I'm interested in. And now I see the other subfolders beneath that one. And once I get to the lowest level of detail, I will see that each file with source code, we see a bunch of them here, are visualized as circles. And we see that those circles, they're different size, right? So here's a small one, a large one. Size is only used to express the number of lines of code, right? So the larger the file, the larger the corresponding circle. The important thing here is always the colors. So that's what I want to talk a little bit about now. So let's zoom out again so we can view the whole code base at once. When prioritizing technical depth, there are always two dimensions that are important. The first dimension is the quality dimension. What does the code look like? Do we have any code smells? Do we have any code quality issues? Any design issues? That kind of stuff. And that's information that you can mostly get out of a static analysis. In CodeScene, we choose a different terminology. So we're talking about code health. So let me click here and I'm going to explain what you see. So now you see that the color changed, right? What you see now is that each file, each one of those circles have been categorized into 3 different categories. And we can zoom in our part here, it makes it easier. Let's zoom in here on DevTools. And you see the legend to the right. So code health is a metric that tells you how easy is this code for a human to understand. So if I as a developer have to work with this particular module, how easy is that going to be for me? Or is it going to be high risk, or will I be able to understand the code? And I can go into more details later when we have time for questions on how this is calculated and what factors are used to determine the code health. But for now, the only important thing is to notice that we have 3 different categories of code here. If we look at the legend, we see that everything that's green, that's healthy code, right? So all of this is healthy code. And healthy code simply means that this is code I can expect to, open up, I can understand it, and I can safely maintain and extend it. The next category is the warning category. So that's yellow here. And warning simply means that there are a bunch of growing code health issues. There are a bunch of design smells and code smells. And unless we are careful, we will start to take on a large amount of technical debt here. And we might end up in the red category, which is the alert category. So the alert category is where we are very confident that there's a high amount of technical debt in that code. And if we want to fix it, it's going to be expensive, right? So anything we can do to prevent our code from ending up in a low code health category is valuable. Now, using code health, we can quickly do an assessment of the code base. So we can immediately see where are the modules with low code health and corresponding where are the modules with a high degree of technical debt. We see there are a bunch of them here in React Reconciler. We also see some of them down here in bench or benchmarks. There are 3 large modules there. What this view cannot tell us is, does it matter? Does those modules with technical debt, do they have a business impact? Are they impacting our ability to deliver software? This is where behavioral code analysis really shines. Because the behavioral code analysis is not only focusing on the code, it also focuses on the evolution of the code. And the way we do that in practice is by hooking into your Git repositories and your version control history. So using version control, we can calculate things like hotspots. So let me show what a hotspot is. I'm going to shift perspective here. And now you see that the colors changed. Some modules are much more red than others. So let me zoom in here. So a hotspot is simply the part of the code where most of your development activity is. And this is measured by counting the number of commits in your version control history for the whole code base and then aggregating that. So what we see here is that this module, React Fiber Work Loop New, a JavaScript file, that's the module with most development activity. And why is that important? Well, it's important because if there's a high amount of development activity, and if there is some technical debt in that code, then there's going to be a very high interest on that technical debt. So you can basically view the amount of development activity as the interest you have to pay on your technical debt. It's the interest rate, right? And this is interesting because now we can start to talk about complex code that we have to work with often. So we want to find the overlap between these 2 dimensions. And one finding I did here immediately was that if we go back to a code health perspective, we see down here in benchmarks, there are 3 highly complicated modules. But if we look at the hotspot perspective, the relevance perspective, we see that there's no development activity in those parts of the code. So maybe it's just a third-party dependency that's being checked in and it's never touched, or it's code that's stable, right? We never need to modify it. So that means we can most likely live with some technical debt in stable parts of the code. However, what we cannot afford is to live with technical debt in the more volatile parts of the code, the parts of the code that are worked on often. So what can we do here? Well, we can dig a little bit deeper. Let's see what we can find. Let's find an overlap between complex code that we have to work with often. Here we go. So here's something, React Fiber commit work. So I can click on that one. And from here, I can get a little bit more information. If you look in the window to the right here. First of all, I see something called a complexity trend. So a complexity trend is simply a behavioral code analysis technique where when we find a hotspot, we go to the version control data, then we pull out each historic revision of that code, and we measure the code complexity at each point in time. And you can basically use any complexity metric that you want, because none of them have a particular good predictability in the small. However, the trends are always interesting. What CodeScene uses is a technique that kind of looks for the nesting depth in that file. And I'll be happy to clarify more about that in the Q&A session later. The way I use this is because I look at the complexity trend and I see that this file has grown rapidly in complexity, particularly lately here. If you look at 2021, you see there's a steep increase in complexity. So what that means is that we have a hotspot with low code health. So we know that it's challenging to maintain that code. And when we work with that code, it gets worse and worse and worse. It adds complexity. So this seems to be a growing problem. Now, if I want to dig deeper, there are several things I can do. I can, of course, look at the code. I can use tooling to help me. I could look at my Sonar results for that file, or I could, if I'm in CodeScene, I can use CodeScene's virtual code review to see what kind of code health issues do we actually have in the code. So I can open that up. I can see where in the code do I have a specific issue, why is it a problem, and get some recommendations on how to fix it so that I can start to plan on improvement and action based on the data so far. However, what you will see is kind of interesting, that when you find these really problematic hotspots, it's simply not realistic to fix all technical debt, right? And even if we know that this technical debt is costing us a lot, we're always going to have this trade-off between improving existing code versus adding new features. So that means we need to kind of find that balance, right? And one way of doing that is by using a behavioral code analysis technique called X-ray. What is X-ray? Well, if we look at this hotspot, we see here, there's a size metric. We see that it's roughly 2,500 lines of code. So it's not that extreme, but 2,500 lines of code is still a lot, and it's highly complicated. So if we target this module as a refactoring target, what's going to happen is that most likely we will work on that refactoring for months, and at the end, we will never ever be able to deliver our changes, because in the meantime, all our colleagues have been adding new stuff to that module in parallel, right? So I always advise against large-scale refactorings. What I advise for instead is to kind of take that problem and break it down into something much smaller. And this is where the X-ray analysis really helps. So let's press that button, and I'm going to explain what you see. So what an X-ray analysis does is that it takes our large hotspot, it parses it into separate functions, and then it looks at the Git log and see where do each commit hit over time, and we sum it up to get hotspots on a method and function level. And this is what I use to find a starting point for technical debt pay down, right? To find a starting point for refactorings. So in this case, I would start to investigate refactoring opportunities in this function, commit layout effects on fiber. And the reason I would do this is because I can see from this data that over the past year, I have made 64 modifications, we as an organization, just to that function. So like at least once a week, some developers impacted by any excess complexity here. And we can get a very quick estimate on the complexity by looking at the final column. So this is a metric called cyclomatic complexity. It's a well-known complexity metric. And the way it works is basically that cyclomatic complexity calculates the number of possible branches in that code. So each time you have an if statement, +1. Each time you have a loop, +1. And as a rule of thumb, you want a low cyclomatic complexity. You typically want it to be around 2, maybe 3, rarely more than that, because then it starts to get challenging for us. And the reason I use cyclomatic complexity so prominently here is because cyclomatic complexity is a pretty good estimate on the number of test cases you need for that function. So the way to read it is that commit layout effect on fiber would need at least 71 test cases to be fully covered. And that kind of tells something about the complexity. The good news are that with the X-ray, we're now down to 300 lines of code. So 300 lines of code is small enough that, you know, we can assign it to 1 or 2 developers and we can make progress on that really rapidly. You know, within a couple of days, we can have a refactored version available. So that means we went from 400,000 lines of code, the size of total React code base. Then we narrowed down to a hotspot with 2,500 lines of code. And using the X-ray analysis, we could get down to a specific starting point for our refactorings with just 300 lines of code. And it's all based on data from how we, as an organization, work with the code. So before I take questions, I want to show you something else, because an interesting thing is always to see how well does a particular technique scale. And I told you that React was roughly 400,000 lines of code. Let's raise the bar a little bit. Let's look at something really large. Let's look at Linux, the Linux kernel. It's one of the world's largest open source projects, right? And we see here that the Linux kernel, if you can read the numbers here, consists of more than 21 million lines of code. And it's being actively developed. That is, the number of developers over the past months are almost 2,000. So if you have 21 million lines of code, 2,000 contributors, who will be able to get the situational awareness? I don't think there's a single person who would be able to reason about that complexity. Besides, it's a code base at that scale. It's always a moving target, right? So it changes all the time. So this is where I think we really need a behavioral code analysis to stay on top of it. So let's look at the hotspots in Linux and see what 21 million lines of code actually looks like. So let me click here. And we see the complete Linux kernel modified and visualized here. So it's the same visualization style. Here we see a drivers package, FS, the file system, the net folder, the kernel itself. You see it's very nicely modular, right, with concepts that align with the problem domain. I really like that. And of course, I can look for an overlap between complicated code that we have to work with often in Linux as well. So I click refactoring targets and I see there are a bunch of them here. Let's see what we find. Here's something interesting. Intel display. So I click on this one. And Intel display, now we really see the use for the X-ray analysis, because even if we know that the Intel display here might be driving our costs via technical debt, we also see from the numbers here that this is a really large module, right? Almost 10,000 lines of code. And no one wants to refactor a code of the, a module of that size. So let's see if we can use X-ray to zoom in on a specific starting point for our refactorings, just like we did in React. Here we go. We see on the candidate here that I would investigate first is Intel setup outputs. Again, modified roughly once per week. And we see that we are now down to 250 lines of code. So within a minute, we went from 21 million lines of code down to a file with 10,000 lines of code, and then down to a specific starting point with 250 lines of code. And of course, my investigation, if this was one of my code bases, would not start here, You know, at some point I need to pull up the code, I need to look at it, I want to look at the virtual code review, and I kind of need to align with the team. What should we do about this? What's the best direction? The thing is that I now have data to support my conclusions, and reality no longer has to be a Rorschach plot. So I hope that this introduction to behavioral code analysis kind of got you interested in all of this. And if you want to dig deeper, before I go into the questions, maybe I should share some resources with you. So let's see here. If you want to dig deeper, I have a bunch of stuff available. I've covered the hotspot analysis and a lot of other analysis in more depth in my latest book, Software Design X-Rays. So if you want to dig deeper, please consider to have a look at that book. I'm also blogging regularly about this at CodeScene.com, as well as my private blog, AdamTornhill.com. And if you want to try this out on a code base, then I can recommend the community edition of CodeScene. It's completely free. Just sign up and point it to a Git repository that you have ownership of, and you can run a hotspot analysis on your code as well. So now I've been really looking forward to see if there are any questions, if there's anything you want me to clarify, or if you want to ask me something about software development in general.
Sure, Adam. So I think while we wait for some of the questions which are coming in, I had a few questions. And first of all, thanks a lot. And it still gives me chills every single time when I see a hotspot diagram of any system. And it's unbelievable how a large project can be reduced to just a few files or few functions which may have technical debt, right? I think I have two questions for you. One question is that you did talk about the change frequency. So what you're saying is that, okay, a module which is seeing a lot of change should be one of the candidates where we go ahead and fix technical debt. So a function that saw 67 or 70 changes in past 1 year. So is there any correlation? Is it just the number of changes, or is there a correlation between number of authors as well? So if there is a function that one person changes as opposed to 10 people changes, is there a correlation over there?
Yes, there is a correlation. So basically, they're very separate. So you can view the change frequencies as the relative importance of a module. So each time someone makes a commit to a module, I kind of view that as a vote for the importance of that module, if we mind the collective intelligence of the organization. Change frequency alone doesn't really have any correlation to quality, right? So you can have modules that are frequently worked on, but are very, very clean and simple to understand. And if that's the case, then you're in a very good situation. But quite often you find out that the most worked on modules are also the ones with the lowest code health. So you really want to find that overlap. When CodeScene prioritizes, we add other dimensions as well to the priorities. One of them is not exactly a number of offers, but maybe, let's see how I can put it. It's more about contributions of different offers. So if you have like a module written by one main developer, then there's lower risk than if you have a ton of smaller minor contributors. And this is pretty well supported by research that the more minor contributors that you have in a module, the higher the risk for defects. And the reason for that is probably because as a minor contributor, you might not understand the whole solution, and you might make a change based on an incomplete understanding. So it's another important factor. Another important factor would be the actual dependencies, right? So if you change this module, you also have to make changes here, here, and here. If that's the case, then the impact is larger of any technical debt. So I hope I managed to clarify.
And I think I have the second question was follow-up question based on this question, which is you did discuss that what we are doing is almost behavioral and psychological code analysis, right? So the underlying root cause of why you may have technical debt is the psychology or the behavior of people. But in the end, in the solution space, what we're doing is we're fixing the code. So it's almost like treating the symptom and not treating the underlying disease, which is behavioral or psychological. So does CodeScene in any way, or forget about CodeScene, are there better ways for us to manage organized teams or organization, which you could look at behavioral changes and not necessarily just code changes?
Yes. But so I actually have, like, I think the whole second part of software design X-rays is about the team dimension. How do we successfully align our teams with the software we're building? However, what I keep coming back to when I dig into these subjects is that it's virtually impossible to separate the organizational design from the design of the code. And this might sound counterintuitive, but what I very often find is that if you have specific technical debt challenges, then that is going to impact your organization as well. And the classic example that I see all the time is that you have a module, and a module in this case, it could be a complex hotspot, it could be a subsystem, and that module is low on cohesion, meaning it has way too many responsibilities. As a consequence, what's going to happen is that no matter how you try to separate and slice your teams, everyone at the end is going to end up having to do some work in that module because it has so many responsibilities, it's so central, right? And if you try to fix this by kind of enforcing a very strict ownership and say that, hey, only team A is allowed to modify this code, what's going to happen is that you're going to increase your lead times because now everyone has to wait for work that's being queued up to team A. So very, very often, I find that the organizational challenges we have can, to a certain degree, be fixed by technical refactorings. But it's a very interesting topic, and I'll be happy to dive deeper into that at another point.
Great. Just to summarize what you said is that the behavior of people can cause bad code, but changing the code can change the behavior as well, because you're separating things out, and then the teams may soon or later start getting the clear ownerships of their own modules.
Exactly.
Right.
So
right.
you do want to have that alignment, right, between what your code looks like and what your organization looks like, so that you can minimize the coordination between different teams, in particular coordination in code that's really expensive.
Correct. I think I have two questions on the chat as well. One that has come from Hitesh Das that says, is there any guidance that you can give us in planning technical debt in parallel to business task for an agile development? I think this is one of the most classic question, right? How do you solve technical debt while other people are still doing development, new features and whatnot?
Yes. So my recommendation here, I have like a rule 0 for managing technical debt. And rule 0 is that don't even start to talk about refactorings. Rule 0 is to put a quality bar on what's already there, right? And the reason I find that this works well is that no matter what level you start at, you never want it to get worse. So I think I met a couple of hundred, tech managers over the past 5 years. And until now, not a single one of them have ever claimed that we want our code to be worse. We want it to be less maintainable. We never want that, right? So it kind of makes sense to use the existing quality as a bar. And what we tried to do was, let me try to share my screen again, was that we tried to build this in as a first-class citizen in CodeScene. So if I go to one of the projects, let's see React here. What I would do is I would look at this part, danger. What's the danger here? Well, let's see, code health decline. So we see that in the React code base right now, there are 8 hotspots that decline in code health. So to me, this would be the action point, right, to prevent this from happening. Because once code has declined in code health, it's usually quite expensive to bring it back up to a healthy level, and it usually doesn't happen without large efforts, and that's where you need all the planning. So using tools that can kind of integrate into, ideally, should integrate into your existing workflows and kind of act as a, as an extra team member, as a quality gate, and detect any code health declines that you have. Because the earlier you can catch it, the cheaper it is to fix. So that would be, to me, the most important decision, to agree upon that quality bar in the organization. Did I manage to answer the question?
Yes. And again, to summarize, what you're saying is the first step is to stop the code from being worse than what it was. So put a quality bar. It could be in Sonar, it could be in CodeScene, and stop the leakage, and then start thinking about fixing more technical debt. I think there's one more question by Alpesh over here. I think this is the one that can kind of start a fire, like a fight between managers and developers. But this one, the question reads, who's responsible for technical debt in your code base?
Yes. Who's responsible for technical debt? This is, I think, what makes it so incredibly challenging to manage technical debt. Because who's actually responsible? Well, you could say that a manager or a product owner have the ultimate responsibility, right? Because they are kind of responsible for planning our work and planning our features. It's very, very rare that the development team owns their own time, right? So very often we have external commitments that we need to fulfill. And at the same time, as a non-technical stakeholder, it's virtually impossible to get a grasp of your technical debt. So it's very hard to make those priorities and say, let's take a step back and pay down the technical debt. So I like to say that we are all responsible, and the responsibility that we have as developers is to make sure that we can communicate that situational awareness that's needed to our non-technical stakeholders. That's our responsibility. And if we manage to share the same picture of what the system actually looks like, where the technical debt is and how it impacts us between the dev team and the non-technical stakeholders, then we were in a very, very good position to have a fruitful conversation around what should we actually do about it. And this is actually where all of this started years ago. So in my previous life, I used to work as a software consultant, who was often hired as a tech lead or a software architect, something like that. And one of my main responsibilities was exactly this, to have that communication with my product owners and business managers. And I found it virtually impossible to have that conversation. I tried static analysis tools, and they were good for my purpose, but it doesn't really tell anything to a manager. You cannot go to a manager and say, hey, we need to fix this because we have a cyclomatic complexity of 200. It doesn't mean anything to them. So that's when I started to look into these techniques that evolved into CodeScene. And what I found is that if you sit down with a non-technical stakeholder and you walk them through the hotspot visualization, you explain what it means. It's usually very intuitive to them. And then you show them the complexity trends, and everyone understands that something, even if they don't know how code complexity is measured, right? If you see something called complexity trends and it goes through the roof, everyone understands that it's not a good thing. And besides, hotspots are a positive message to non-technical stakeholders. They like them. And the reason they like them is because what a hotspot analysis tells them is that, hey, we don't need to fix all that code. We don't need to fix all those 2 million lines of code. What we need to do is we need to focus on this and that. I can do that. That's predictable. So I think the main contribution with behavioral code analysis, that behavioral code analysis can actually act as this bridge between the tech world and non-technical stakeholders.
True, I think, and you put it correctly, everyone loves these graphs, right? The ones that are going up. Once they see a graph like that, they buy into the concept. I think we have two more questions over here. One is, does over-engineering or oversimplification of code also create tech debt? So if I may call it, yeah, go ahead.
Yes, it does. It does. In a way, it does. It's typically different because the root cause is different, right? It's not about taking shortcuts. It's simply that you went too far with the design, typically with separations of concerns and stuff like that. In my experience, it's something we talk about a lot in the software community, right? Every single discussion around code complexity, you end up with like two polar opposites, right? And in reality, and this comes from someone who has analyzed maybe 300 code bases over the past years. It's something you almost never, ever see, right? We don't have that as a general problem in the tech industry. Our problem is the opposite, that our code is too complex. That said, on the rare occasions that I came across it, what typically tends to happen is that the complexity will still be there, but instead of being centered inside a specific file or function, it kind of tends to be distributed, right? So all the complexity is in the connections, the interconnections between the different design elements. And to me, this is often a more challenging problem to address because it's so incredibly hard to understand how the solution fits together. So what I do in these cases is that I use a different behavioral code analysis technique called change coupling. So if you have access to my book or you go to my webpage, then you can read a bit about change coupling and see how it can help you with that. So I hope I managed to give my perspective on the question.
Sure, Adam. It does make sense, and I hear this a lot of time that people who by design may not do good coding. If they start doing coding in microservices, they now create distributed complex code. So I think you just have to find the right balance, whether it's a monolith or whether it's a microservice, and keep moving forward. I think there's one by Hardik Prajapati here that says there are so many different metrics for to measure code health. Do you have something specific that you follow or is your favorite?
Yes, so let me paste the link for you on the chat. I'm just going to dig it out. Let's see here. Yes, there are so many different metrics, and all of them have their flaws. So let's see here. You should now have a link in the chat that you can read more about code health. So what I did basically when we start to develop CodeScene, we kind of realized pretty quickly that we need some kind of quality measure, right? I just wanted to avoid the word quality, so I choose code health instead because quality is exceptionally ill-defined. So the challenge you run into when you try to measure quality of software is that there's not a single metric that can capture a multifaceted concept like software quality. So instead, if you look at the research, the most promising approaches is to measure many different aspects separately and then try to combine them. So that's what CodeScene does with code health. We measure, depending on programming language, 20 to 25 different factors. And then we have algorithms that are trained to weight them together depending on program language and context and whatnot to come up with these code health categories. But it's not a single metric, it's an aggregated metric. And you can read more about how it works and the use cases on the link I shared with you. What I found interesting was that we actually got some research confirmation a couple of weeks ago. So CodeScene is not a security tool, but there were a bunch of security researchers that studied concepts like hotspots and code health from a security, from a vulnerability perspective. And what they found out was that low code health correlates with security vulnerabilities as well as hotspots, right? So it's pretty interesting that the stuff you have seen today, it's not only about this financial perspective, about making things more efficient. There might also be a security dimension to it that I find very, very fascinating.
Great, thanks a lot, Adam. Adam, I'm not sure how you're placed time-wise. I have one more question. Do we have time to take it or?
Yeah, sure, I have time.
Perfect. So I'm going to paraphrase a question asked by Rushali Parikh over here that, so what seems like a perfectly good solution in the beginning, as you keep adding more features in it, now it will build technical debt with time, right? So what was perfect earlier has now slowly is building technical debt. So would it not be a best practice to like have a continuous process along with new development to solve technical debt? So maybe you're adding a new feature, you're looking at a file and you also refactor it before you add a feature. So I think it goes back to leaving the campsite cleaner than you found it kind of a.
Yeah, definitely. I absolutely agree with that. So technical debt management, it's not something that you start with when you already have the problem, right? It's something you want to have from day one. And it's actually scary how quickly code can deteriorate. So over the years, I've looked at several legacy migration projects. And there's always this hope, right? And hope is good. That's why we do stuff, right? So we start a new code base, and now we're going to avoid all the problems we had with our legacy system. And things usually start to look pretty good for the first months. And then typically at some point something happens. You know, either there's some kind of deadline, some kind of demo that needs to happen, or you put the first like customer in. And after that, what tends to happen is that if you continuously measure your technical debt, you see that it starts to peak very, very rapidly. And it's very unfortunate because once you have taken on technical debt, it's expensive to act upon it. That's when you need to have all these meetings, then when you need to have alignment and agreements and whatnot. So anything you can do to avoid it in the first place, or when you take on technical debt, make it a very, very conscious decision. So the clients I work on that work with legacy migration projects, they use CodeScene from day one, right? And already after a couple of weeks, you can start to see the first patterns. So I highly recommend practice as managing technical debt from the start.
Great. And I think, Adam, I have to add to that answer also that the how do I say it? The craft of fixing technical debt has to be learned by everyone. Otherwise, what happens is, and because as you correctly said, it's a behavioral thing. If you had like a separate task force, you can have a task force to train everyone to create that behavior. But if you had a separate task force, I think people create mess faster than a task force can clean it. So just want to add to your answer that yes, it not only is try to continuously improve the state of the code, but also have that behavior instilled in almost the entire team.
That's a very good observation. I also think what happens if you have a task force, if it's for support issues or if it's for fixing technical debt, I think what you do is you cut away a very important feedback loop. Because now as a developer, right, I can just go ahead and I never hear anything negative about my code because someone else is there to pick it up and fix it, right? So I think we miss an important opportunity to learn. So I absolutely agree with that.
Awesome. Well, thank you so much, Adam. I think what I'm going to do is one of the organizer Arohi or Rushali, if you could go ahead and close the loop.
Sure, thanks, Sapan. Adam, thank you so much for joining. I think this talk was very, very intriguing, more so for the developers, but even for a business person like me, there's a lot to learn from you and from everything you've done in your career around behavioral code analysis. So I'm sure we'll be all looking deeper into this and hopefully using it in our daily lives going forward. So thank you so very much for doing this. We will be chasing you again to come back here and talk to us more again and again, hopefully. We would love to have you here again. So thank you very much, Adam.
Definitely. And thanks a lot, everyone, for attending. And thanks for inviting me. And thanks for all the questions. Really appreciate that. And wish you all a really great day.
Thank you. Thanks, everyone, for joining. And do take a look at Meetup every once in a while. We have another call coming up, or another meeting, another event coming up, which will be hosted by Narendra Pathai from eClinicalWorks. And he is going to be doing a very hands-on session to for anyone to learn TDD or test-driven development. So look forward to that, and then we will be announcing new events shortly. Thank you all.